Introduction. My name is Peter Hayes, and I'm a principal technologist here at HBM nCode, responsible for fatigue analysis methods development. And I'm here today to give you an update on something we've been working on over a period of a few years now, which is fatigue analysis of short fibre reinforced injection moulded thermoplastics. Okay, so this is the agenda for the webinar. I'm going to begin with a short introduction and then outline some of the challenges that composite materials present for the fatigue analyst. We'll then look at how we can start to address some of those challenges for short fibre reinforced thermoplastics using what we call a through process modelling approach. We'll also have a look at some of the challenges these materials present as regards physical testing and how we're addressing those challenges too. And then I'll summarise what we have implemented in nCode DesignLife before winding up and taking some questions. So first of all, you may have noticed this word Prenscia appearing at the top of my slides. This is a new thing, and Prenscia is a strategic segment of HBM which has been created, and it's basically by bringing together nCode and ReliaSoft. And together, basically, ReliaSoft is all about reliability and managing risks and warranty costs and so on. And nCode, you're probably familiar with, it's providing engineering, data analysis and management tools, and in particular focusing on fatigue and durability, which is of course what I'm going to be talking about today. Okay, so just a very quick reminder of what the nCode product range is. It comprises 4 products now: nCode DesignLife for doing fatigue analysis based on finite elements, nCode GlyphWorks, which does data processing with a bit of a durability focus. We also have a relatively new product, nCode ViSys, and for doing vibration and acoustic analysis, and nCode Automation, which is a data management tool. Okay, and the focus of my attention today really is when I'm talking about short fibre reinforced thermoplastics, it's all about fatigue analysis in nCode DesignLife. So let's go on and outline some of the challenges that working with composites presents for the fatigue analyst. Anybody who's had anything to do with nCode over the years will be familiar with what we call our 5-box trick. So this is a simple picture of a fatigue analysis which comprises 3 inputs. The inputs being the geometry as represented by a finite element model here that we use to calculate the transfer function between the applied loads and the local stresses and strains that drive fatigue damage. We have an applied loading history. Here in my picture it's a single channel, but it can be, the loading history can be as complicated as you like, include complex duty cycles, multiple channels, multiple modes, etc. And then the third input is material information, normally in the form of parameterized curves, stress life and strain life curves. And then, given that those 3 types of input information, we can carry out a fatigue analysis, and then typically we look at the results in terms of contour plots of damage or life or tables. So this kind of process is pretty well established and trusted for metallic components. So just to continue setting the scene, I'll just give you a very quick summary of what metal fatigue is. Metal fatigue is the process of crack initiation and then crack growth under cyclic loading until the cracks reach critical size and are big enough to cause failure. So crack growth is driven by crack tip plasticity resulting from cyclic stresses. But what we find is that in metal fatigue, that the fatigue lifetime is very often dominated by crack initiation or by the growth of very small cracks. And this is why we can often make very useful predictions of metal fatigue by using a local approach, for instance, based on local stresses and strains. Now, unfortunately, composites also fatigue. If you look at the picture in the middle of the broken wind turbine blade, this is a picture that was actually taken out of our office window. So composites definitely fatigue. But their behaviour is quite a lot more complex. We tend to see multiple damage mechanisms, matrix fibre, fibre failure, fibre pull-out, delaminations. There's also a major effect of the manufacturing process. So we often see failures initiating at edges, manufacturing defects, or sometimes it's impact damage. And rather than being dominated by one crack or a small number of cracks, very often the damage is diffuse and progressive, consisting of lots of micro cracks. The other thing is that these materials are in general inhomogeneous, highly anisotropic, and very often they are very sensitive to the temperature and sometimes also to environmental factors such as the relative humidity. And it's this sensitivity to the manufacturing process in particular that means that when analysing these materials, we need to use a through process approach. Now, a composite is pretty much anything that is made out of more than one sort of stuff. But in this presentation, I'm going to concentrate on one particular type of composite, and that is short fibre reinforced thermoplastics. So these materials are made into components by a process of injection moulding. So they'll normally be a pelleted feedstock that's fed into a hopper, melted, and then squeezed into a mould. The most common matrix materials are probably polyamides and polypropylenes, and normally reinforced with short glass fibres. And when I say short, I mean fractions of a millimetre in the finished product. So these kinds of materials are very widely used, for instance, in the automotive industry, but also in electronics, sport leisure applications, many different applications. And I guess the good news for us as analysts is that the failure modes of these are not so complex as they are for continuous fibre laminates. But nevertheless, they're still very anisotropic, and I mean that the properties can vary easily by a factor of 2 or more in different directions. And so the manufacturing process and the anisotropy that produces are still very important. And that is why when analysing these materials, we need to use a through process modelling approach, which basically means that if we want to predict the structural performance of parts made from this kind of material, we have to simulate all the way through, including the manufacturing process, as we're going to see in the following section. Okay, so here we have an example of an injection moulded dash or instrument console, and when this is injection moulded, the flow of material into the mould, it more or less aligns the fibres in different parts of the structure, so that we end up with properties that are inhomogeneous, different everywhere, and they're anisotropic depending on the flow directions. So that makes life much more difficult for the analyst. We've got different properties everywhere in the model. On top of that, the materials tend to be pretty sensitive to the temperature, and some of them, for instance, polyamides, are very sensitive to the environment, the moisture content as well. And typically, behaviour is, in the fatigue regime at least, is predominantly viscoelastic. It's a bit worse than it looks in that picture, actually, because not only do we get a spatial variation in the fibre orientations across the model, but if we look through the thickness, we also get considerable variation through the thickness of the component due to what we call a skin core effect, where in general you get alignment of the fibres with the flow direction, but it's different on the surface, and you also tend to get a core where the fibres tend to be aligned transverse to the flow. So if we actually want to analyse this kind of component properly, we need to know what the microstructure is like at every point in the model. And in particular, we need to know the distribution of the fibre orientations. And this fibre orientation distribution can be described by a second-order tensor, which we call the fibre orientation tensor. And these tensors can be predicted by moulding simulation tools such as Mouldex 3D or MouldFlow. And you can also measure them either using CT scans or optical techniques. So in some of the work that follows, I'm going to show you some measured orientation tensors which have been measured using an optical technique by Professor Baird's team at Virginia Tech. You look at the picture on the right, it's a cross-section through one of our 2mm test plaques, and you can see that each fibre creates a shape where it's cut through by the section. So if we look at the aspect ratio of the ellipsoids, the ellipses that these fibres make when we cut through them, we can tell what their orientation is. So I think you can see clearly here that there's something different going on in the central region of the plaque, where the fibres are aligned transverse to the flow direction compared to the rest of it. So that's the skin core effect. The moulding simulations can tell us what these fibre orientation tensors are. Just to give you an idea what this means, if you had the fibres completely aligned in the X direction, then you would get a tensor where you had a 1 in the top right left-hand corner. If you have a fully 3D random distribution of fibres, all the diagonal terms will be the same, and they would be 1/3. So based on this, we can then predict material properties, but we also need to know some other material information. In particular, we need to know the fibre volume fraction and the fibre aspect ratios, and also the properties of the matrix and the fibres. Okay, so this next slide shows what the whole process looks like. So in order to carry out fatigue simulations, you need to start off by doing a manufacturing simulation using one of the moulding simulation tools. And the key piece of information we need out of that is the fibre orientation tensor A. Given that information, and if you also know the fibre volume fractions and aspect ratios and the elastic modulus, Poisson ratios of the fibres and the matrix, you can then use homogenization techniques such as the Mori-Tanaka method to calculate the material properties. And in particular, by that I mean the elastic stiffness matrix. And that process is repeated at every integration point of your FE model. So there are a number of software tools that can help you map those properties onto the FE, including the moulding simulation tools, or alternatively additional software such as Digimat. Digimat can also take things one step further if you want to do nonlinear analysis by using the user material definition architecture of the FE and essentially making a nonlinear material plugin. But for the work I'm going to talk about today, we're just really considering elastic behaviour. So this is all this has to happen before it gets to nCode. This is where we come in and we start to do our fatigue simulation. We add in the mission profile or duty cycle, in other words, the applied loads. And we also need to plug in a fatigue material model. Because the material is anisotropic, we may well need the fibre orientation tensor again here. And in order to calibrate the model, we're going to have to test coupons that have different orientations relative to the fibre orientations. Because the material is anisotropic, we are likely to need to do that in order to calibrate our model. So assuming we can put all this together, and I'll go on to the specifics of the material models later, we should be able to do some kind of simulation and get a life prediction. Okay, so that's the whole process. So in the next section, what I'm going to do is to focus on this part and to consider how is it that we can calibrate our material model based on our coupon tests, and there are some significant challenges in doing this, as we're about to see. Okay, so material characterization challenges. So just to set this in context, I'm going to go back again to what we know about characterizing metals first. When we want to characterize a metal for fatigue, for example, if we want to use the local strain approach, we test specimens such as the one illustrated in the picture on the top right. So this is a nice, smooth, cylindrical specimen with gentle radii, and it's tested in strain control as defined by the clip gauge that's attached to the side of it. So when we analyze data from these tests, we can reasonably assume that in the central gauge section of this specimen, that the stress and strain are quite uniform. So when we want to know what the stress is, we can calculate that from force over cross-sectional area, and strain is simply extension over length. And most of the time we can also make a reasonable assumption that the material is behaving in an isotropic manner. And then we process the data to give what we call material parameters by fitting stress, strain, and strain life curves through the data. And the parameters that we come up with from this kind of fitting exercise, we normally call these material parameters, even though what we've actually tested is a coupon thing. Now let's see how this approach changes when we start to look at engineering polymers. So first issue is, what should we test? Well, ideally we would test injection molded coupons because we can make them cheaply and easily, and that represents the manufacturing process of the components. But if we want to study different fibre alignments, that won't work, because when we injection mold coupons, the fibres will be aligned with the coupon. So we end up having to machine specimens from plaques. So the next issue is that unlike the metals, our test coupons are inevitably inhomogeneous and anisotropic because of the skin core effect, and this leads to a non-uniform stress distribution. And what this means is that even if we want to get properties from our simple specimen tests, we have to do some reverse engineering based on a proper understanding of the stress distribution in the coupons, which means doing manufacturing simulation and detailed FE analysis of our coupons, even to get the material properties. So we need to, the other thing I should mention is at this point is that we are still looking at multiple different fatigue models. So we have 3 basic classes of model that we're looking at the moment. We have a simple interpolation method. We have Digimat's high cycle fatigue model, which we also connect to, and we also have an elastic strain energy approach. So far, we've just we've been working on this, and I've worked mainly on the elastic strain energy approach, but we will need to calibrate these other models as well. And I'm going to just show you a little bit of the work that we've done on an internal project, and this is based on a polyamide, a PA66 with 30% short glass fibres. So the first problem we faced was to make some test plaques from which we could cut specimens. Our first set of plaques were rather warped, and so we had to optimize the shape of them, which we did by changing the injection area. And the aim here was to try and achieve a straight flow front. So the pictures that I'm just putting up at the bottom of the slide now show the flow front as the material flows into the mould at successive times through the injection process. And so what you can see is that by the time the material is flowing into the main square part of the plaque, we've got a very nice straight flow front that gives us reasonably uniform properties across the plaque, if not through the thickness, and that also minimizes the amount of warpage that we get. So these simulations were carried out in Mouldex 3D using their IARD RPR model, and that also allows us to predict the material orientation tensor, at least in a first pass. What we did then was to actually have some measurements of the material orientations carried out as well. This was work done at Virginia Tech. We did measurements at 9 different points on our test plaques. At each of those points, we had the orientation tensor measured at 13 different points through the thickness, and all the data was averaged across 6 test plaques. So in the table on the right, you can see a summary of the orientation tensor components at the center of the plaque at 13 different points through the thickness. And at the same time, we've also had the fibre length distribution determined as well from the center of the plaque. So when you have this measured information, that allows you to refine and optimize the moulding simulation to get better results of that. There are some parameters in the IARD RPR model that can be tuned if you have experimental data and allow you to get a nice match between the predicted and measured orientation tensors. So what we're looking at here in these plots are the 3 diagonal terms of the orientation tensor in each plot. We have 9 plots representing our 9 positions on the plaque, and as we go from left to right across each of the plots, we're looking through the thickness of the plaque at the orientation tensor. The solid lines are the simulation, and the blobs with the little bars on them are the measured data. So this is the most important one. This is the comparison of the predicted and measured orientation tensors at the middle of the plaque, which is where we cut the center of our specimens from. So what we've done then is to machine specimens from these plaques in 3 different orientations, 0, 45 and 90 degrees to the flow, and to make our test somewhat representative of real life. Because we're using a polyamide, the condition is very important, that is the moisture content. So ours has been conditioned to 50% relative humidity. We've also carefully controlled the ambient temperature of the tests to 23 degrees C in this case. So, given all that microstructure information, what I've done next is to take the microstructure information and to combine that with a knowledge of the elastic modulus and Poisson ratio, both of the matrix and the fibres, taken from data sheets gathered from the internet. And then I've used Digimat in this case to do the homogenization to predict the, and from that what we can do is we can predict the anisotropic material stiffness matrix for input into the FE. So there's a number of ways that you can put this information into the FE. That you can use features of the moulding simulation to map stiffness matrices onto the FE input deck. You can use additional software packages, or you could use Digimat as a plugin to embed the material model in the FE. For the work that I've done here, I've done it manually. That is, I've taken the manually calculated stiffness matrices using Digimat and applied those from the 13 measured section points to 13 layers of a solid FE model of the coupons using ANSYS. So I've manually inserted the stiffness matrices for each layer. So what I'm now going to do is to have a look at the finite element results. We're going to look at the stress and strain fields for the coupons for the 0, 90 and 45 degree orientation. So let's start out by looking at the 0 degree specimens. So these are the stress analysis results. If we look at the face of the specimen, it doesn't look too bad, though there's clearly a bit of a stress concentration towards the end of the radii. But if we look at the edge of the specimen, we can see very clearly that we get some hot spots and we get some very big differences in the stress through the thickness because of the skin core effect. In effect, what our simple test coupon is doing is behaving like a laminate. And if we move on to the 45 degree specimen, again, now you can see very much the effect of changing the orientation of the material. And you can see that as you try and pull this specimen, it tries to shear laterally. And again, when you look at the edge of the specimen, you can see that the through thickness behaviour is quite complicated due to this skin core effect again. And finally, if I look at the 90 degree specimen, that looks like quite a nice stress pattern. But if I look through the thickness, you can see the middle lights up. This is because in the 90 degree specimen, the strongest alignment of fibres is that very thin layer in the core. So I think you can see from these simple analyses that the mechanical behaviour of this coupon cannot be properly understood if we only plot, for example, net section stress against life or net section stress against strain. Okay. So is this FE reliable? So well, in order to answer that question, we've done some comparisons with the tests. So we've carried out tensile tests, conventional tensile tests. So this gives us a stress strain curve. If we look at the slope of this stress strain curve, that gives us an effective average modulus for the gauge section of the specimen. And what I've done here is to predict the stiffness of this gauge section of the specimen using the FE based on my homogenization and all the individual properties. And the table at the bottom gives you the comparison between the FE and the tensile test results, mean tensile test results for the 0, 45 degree and 90 degree orientations. So I'd draw two things to your attention. One is that there's a very good correlation between the FE and the tensile test, and the other one is that there is more than a factor of 2 in stiffness between the 0 and the 90-degree coupon orientation. So anisotropy is a very real issue for this type of material. We also made some attempts to correlate the strain field by using digital image correlation. We had some issues with signal to noise ratio, so I wouldn't say that this is very quantitative, but it does at least confirm that we are our finite element analysis is predicting the right kind of strain field. Just very quickly, we can also see this plot shows some of the typical hysteresis loops that we get off our tests. We monitor the stress as well as strain when we carry out fatigue tests. And because the material is viscoelastic, you don't see the same kind of hysteresis loop that you see for metals. You see something that is pretty much an ellipse, typical of the viscoelastic behaviour. You get a little bit of cyclic softening throughout the test, and you see just before failure, you see very distorted hysteresis loops because of the large amount of damage in the specimens. Okay, moving on. So let's have a look at some of the our fatigue test data. So these are the some of the raw fatigue test results. So these are SN curves that are presented in the conventional way. So I've plotted the vertical axis being the net section stress range, and these curves are quite typical. We get nice straight lines on log axes, and the 0-degree specimens, not surprisingly, are much the strongest because they have most of their fibres aligned with the loading direction. And we see the 45-degree and 90-degree lines lie fairly close together. But my point in showing you all the stress plots that I've shown you before is to say that we can't really understand or interpret these curves properly unless we bring the FE into play. So, for example, I think if we think that some damage parameter at the most critical location in the specimen is what's going to control its life, then we should use our FE to turn this conventional SN curve into curves that correlate life using the local value of the damage parameter calculated using the FE. So this is what we've started to do. And the easiest one to do, because it gives you a unique critical location in the each specimen, is the strain energy density approach. So ideally, that approach, if it works well, should allow us to collapse our 3 distinct neck section stress life curves into one local strain energy density life curve. So here's my first attempt at doing this. So now what we're plotting up on the left-hand side of the axis is the strain energy density at the most critical point in the model as predicted by the FE. So we've used the FE to convert our net section stress to local strain energy life curves. And what you can see is that compared with the last plot is that our data is starting to fall into a nice scatter band, except that for the 90-degree specimen, the points are a little bit on the high side. So this looks quite promising. But one of the things we haven't addressed here is quite a well-known phenomenon in fatigue, which is the stress gradient or support effect. And when we look at the 90-degree tests in particular, so what I've plotted up on the right-hand side here is the strain energy density parameter for a tensile test in the 90-degree specimen orientation, you can see that the critical area is just this very thin layer of elements in the middle of the specimen. So in reality, using the stresses directly from there could be a little bit pessimistic. And so what I've started to do is to, rather than taking the stress from one critical location, is to use a simple averaging domain approach. And when we apply that, our data starts to fall quite nicely into one scatter band. These are very preliminary results, so we've got quite a bit of work to do, I think, to refine this approach. But even so, just using the local strain energy density looks quite promising. Okay, so I'll just summarize a few points about the material characterization. First point to make really is that we don't test materials. What we actually test are structures, and in terms of these materials, the structures actually have quite complicated behaviour. So that means if we want to derive material properties from these tests, things that we can transfer to other simulations, we need to reverse engineer those properties from our coupons, taking into account the manufacturing process on the coupons and a detailed stress analysis. Next point I'd make is that the strain energy density parameter does look quite promising. One of the features of this that's quite nice is that if it does work well, we should only have to test one orientation, and we could test molded coupons. So that would offer the possibility of considerable cost reduction when it comes to characterizing the material. We've got a bit of work to do on the averaging domain approach, and the work in progress is reverse engineering of SN curves for the other approaches as well. That is for our simple interpolation method and the Digimat high cycle fatigue method. So I'm going to explain these a little bit more in the next few slides. Okay, so this is where we actually get around to describing the implementation of the methods in nCode DesignLife. So a bit of a boring slide here. First of all, in terms of reading finite element models and results, the relevant features here are that we can now deal with models which are either layered composite shells or solids with a layer representing each layer. We can read standard FE results, so stresses and strains from the models. We also work quite closely with Digimat, so that if you run an abacus or ANSYS analysis which has been strongly coupled with Digimat, one of the ways that can write the results out is, rather than the normal stress and strain data sets, it can write them out as state variables, so we can read the stresses and strains from there as well. The other piece of information we need from the model is the orientation tensor information at each of the calculation points. We've then got two analysis engines. We've got the short fibre composite analysis engine. So this uses an SN approach with anisotropic material properties, which are a function of fibre orientations. And we've also got a new strain energy density analysis engine. This is still a beta test version at version 12. We'll be making a full release of it as soon as we have a little bit more data to provide to back it up. I'll give you more details of both these engines in a minute, but there are also a couple of pre-configured glyphs available. Okay, so let's look at a few of the calculation details now. First of all, one component of all our calculations that is very important is multi-axial assessment. In general, the interaction between anisotropic layers in a composite component can mean that you end up with multi-axial stresses, even if the external loads are rather simple. Sorry, I've skipped ahead a couple of slides there. Multi-axial assessment allows us to identify whether we're dealing with a proportional or non-proportional loading, first of all. Now, most cases will turn out to be nearly proportional. And it could also allow us to identify the stress state at any location in a model, including the dominant stress direction. And finally, for the large number of cases that turn out to be nearly proportional, it also allows us to approximate the stress history as the product of a scalar and a tensor that represents the average stress state. So this gives us some very efficient processing options. If this sounds rather complicated, it's actually very fast, and it's so fast that we repeat this at every calculation point, every node or element that we're considering in the model. Just to give you an example of what I mean by proportional and non-proportional, if I plot the stress components out of a time history, this is sigma x, sigma y, tau xy, and I get a plot that looks a bit like this one in the top left, that would be a near proportional loading. Whereas if I get one that looks like the plot bottom right, that would be typical of a non-proportional loading. Fortunately, a lot of our cases turn out to look very much like the picture in the top left. If you look at the stresses on the bottom right, they're very, very small. Okay, so let's get down to some of the details of how the engine then does the fatigue calculations. We have two different basic models. There's what we call our simple interpolation model. Now this is based on the share of fibres that's aligned with the local stress. And by the local stress, I mean either the largest principal stress, or if we're using a critical plane approach, that will be the normal to the critical plane. What does this fibre share mean? Well, basically, it is a resolution of the orientation tensor in the direction that we're looking at. So, for example, if I had a fibre share of 1, that would mean that all my fibres were perfectly aligned with the loading direction. If I had a fibre share of 0, that would mean that all my fibres were perfectly at right angles to my loading direction. So this gives us a number between 0 and 1, and what the software does is at each location it compares the stress direction with the material orientation tensor to determine this fibre share number, and then uses it to interpolate between a set of SN curves. So that means that effectively what we're dealing with, what we're doing is predicting a unique SN curve for each location, depending on the loading direction relative to the fibres. So that's the simple interpolation approach. Normally you try and do it using principal stresses. Critical plane calculations may become necessary if you have non-proportional loading, but this is an area that definitely needs more research. We suspect that our simple critical plane approaches are going to end up being rather conservative. And one other thing I should add is that with composite materials, you can't guarantee that as you more or less can with a lot of metal examples, that cracks will start from the surface. They may well start within the body of the component, where the stress state could be a full 3D stress state. And so if we're going to do critical plane calculations, we have to search over a sphere rather than just in a plane, which means a lot more calculations. Okay, so that's the simple interpolation approach. So the next method that we have is we also have an optional link to the Digimat fatigue model. I think they call it their high cycle fatigue model for short fibre composites. In order to do this, you will need the relevant Digimat licenses to make this work. So this method also creates a unique SN curve at each calculation point, but in this case, rather than just taking into account the stress direction, it takes into account the whole state of stress. It takes advantage of our ability to use the multi-axial assessment at each calculation point to partition the stress history into a scalar multiplied by a normalized stress tensor. And this normalized stress tensor, we can hand that over to Digimat, and we basically call out to Digimat at every node or element, and they compare the stress state with the orientation tensor and use their fatigue model to give us back a unique local SN curve, or more recently they can also give us a unique Hague diagram for each calculation point. And then we can use that in a conventional way to do our rain flow cycle counting and damage accumulation and get a life estimate. So this is again very fast and efficient. Calling out to Digimat at every node or element might sound potentially expensive computationally, but it isn't. It seems to be no computational penalty compared to doing this internally. Just a little word about the Digimat model. I don't have time to go into the details, but it's essentially using a Tsai-Hill criterion at a pseudo grain level. Again, you have to calibrate this model based on tests in 3 orientations. Finally, we have our new strain energy density analysis engine. This is based on the work of Bert Klimkite. And the basic premise is that for a given material, we can correlate fatigue test data for different fibre orientations and loadings based just on the elastic strain energy density. And it's a method that seems to work quite well, basically because the directions in which a material has lower fatigue strength are also the directions where it's less stiff. So one of the big, as I mentioned before, one of the big advantages of this method is that if it works, we should only have to test one series of specimens to characterize a material rather than 3 different orientations. There are a number of different options in here. There's a principal strain-based approach, critical plane-based method, combined normal and shear critical plane, but probably the best method, particularly if you've got nearly proportional loads, is the proportionalized stress approach. This works by projecting the current stress point onto the best fit line that gives you the state of stress, and then we can rain flow count this proportionalized stress to find the turning points of each cycle and the load ratio, and by looking at the largest strain energy density value that occurs during each cycle, we can calculate and taking into account the R ratio, we can calculate a strain energy parameter. I know I'm going over this rather quickly, but if you're interested in the details, they're all documented in the online DesignLife documentation. So finally, this is just a screenshot. At the moment, we still could do with, I'm hoping later this year that I'll be able to show you some more interesting validation cases, including some actual components. Okay, I'm going to go to my concluding remarks and take questions in a minute, but first of all, I just wanted to acknowledge a bit of the help that we've had from some other people in putting all this work together. So when it comes to moulding simulations and advice, we've had a lot of help from MouldX 3D people, from Cortex System. LabVision helped us with the digital image correlation, Virginia Tech with microstructure measurements. The FE was carried out using ANSYS. Digimat supported us by allowing us to use Digimat for the homogenization. All the physical testing, however, was carried out in-house at our advanced materials characterization and test facility. Okay, so just a few concluding remarks then. So first of all, fatigue analysis and characterization for fibre reinforced thermoplastics is pretty challenging and requires some commitment, in particular to get these fibre or pesky fibre orientations included in the simulations. The DesignLife has got a range of options now that are available to address some of these challenges, but I would emphasise that this is not yet a mature science, so we're continuing to work on it. We've got an ongoing program of research and development to refine and improve the methods and to improve the material characterization procedures. If you want material characterization, we are very happy to take that on at the AMCT facility. Okay, so that's about it. I would just like to turn it over now to